Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are looking at electron configuration. So we're asked to write the 4 quantum numbers for an electron in the 6p orbital. Well, if you recall from our previous video on atomic orbitals, you will know that we can find from the denotation of 6p what our principal quantum number and our angular momentum quantum number is. So the 6 in 6p signifies that n is equal to 6. And the p, if you recall, that s is when L is 0, p is when L is 1. So we know that L is equal to 1. From there, we need to write out all the quantum numbers. And I find it easiest to just go ahead and make a tabulation, a table, if you will. We need to do all 4 now. So we've got N, we've got L, we've got M sub L, and this last section will be our M sub S. So let me write those down so we don't forget. All right, so that's our principal quantum number, our angular momentum quantum number, our magnetic quantum number, and our spin quantum number. So from there, we're simply going to write down the different configurations. Now, how many do we have? It's kind of a conceptual question. You could just simply add up all the possibilities, but you could just as easily look at it in terms of, for every L, for this particular case, there are going to be 3 M sub L's. There are going to be 3 possible magnetic quantum numbers. And of those, there are going to be 2 spin quantum numbers, which means that we're going to have a total of 6 entries on here. So let's write those out. 1, 2, 3, 4. And for each one, we will consistently have our N and L being 6 and 1 respectively. So when M sub L is 1, MS can be plus 1/2, or S can be minus 1/2. And again, we do that with 0 and -1. Plus 1/2, minus 1/2. This may seem a little tedious, but it's also good practice. It gets in your mind what exactly it is that you're looking at in terms of the existence of electrons within a certain orbital. So looking at this, how many electrons would you expect to be in the 6p orbital? You'd expect 6, right? And in each of those, in that orbital, you have these the M sub L, which would be almost like a suborbital, and then in those suborbital you would have these 2 spins, these 2 electrons that can take that spot. And that'll show up later on when we're talking about the Hund rule. But the other thing to consider here is there's a reason why we don't write 6, 1, 1 plus 1/2 twice. And the reason we don't, the reason we know specifically that there's only going to be 6 is because of the Pauli exclusion principle, which states that no 2 electrons can have the same 4 quantum numbers in an atom. So when you're looking at this particular example, you know that there's only 1 electron that satisfies the 6, 1, -1, -1/2 as the 4 quantum numbers. There's only 1, which means that we can narrow down the number of electrons and what they're doing in any given moment. at least at this stage. And when you get into molecular orbital theory and such, it becomes a little more complex. But as of right now, this right here explains the number of electrons and how they fit into the atom. So let's look at our next one. It asks, what is the maximum number of electrons that can be present in the principal level of n equals 4? So our principal quantum number is 4. And you can very easily do this by referring back to our previous video where we discussed how to calculate the total number of orbitals in a given a principal quantum number. We can do that just the same with the total number of electrons. We simply multiply it by 2. So in this case, it's just going to be 2 times n squared, which is 2 times 4 squared, which is equal to 2 times 16, which is equal to 32. Now, if you wanted to, you could go through and tabulate all that, but I believe we proved pretty accurately the equation in terms of atomic orbital in the previous example, and I feel it would be a waste of time to go ahead and prove it in terms of electrons, simply because if you prove it for orbitals, you know there are 2 electrons per orbital, then you know that this is only going to be 2 times n squared. So in this particular case, we're just going to accept the fact that it is 32 as the total number, the maximum number of electrons that can be present in that principal quantum number, or that principal level. Our last question, or our last problem, states a carbon atom has a total of 6 electrons. Write the 4 quantum numbers for each of the 6 electrons in the ground state. So what is the ground state? Well, let's look at what that looks like. You'll often be asked to list this out as an electron configuration of a certain type. There are a couple of ways of doing electron configurations. This one is probably one that's going to occur regularly, so it's good practice to figure this out. So if we were to imagine a periodic table of elements, you would know that you have your s orbital, your p orbital, your d orbital, and your f orbital. Your s orbital, you would start with 1s, and then you'd have 2s, and then you'd have 2p. But looking at 2p, you could theoretically divide 2p into several groups. The magnetic quantum numbers, correct? So you have 2p sub x, 2p sub y, and 2p sub z. This kind of indicates that if you look at the shape of the p orbital, it is kind of like a barbell or an hourglass. And this would indicate that hourglass being positioned in the various directions in space. So you have the hourglass going along the x-axis, an hourglass going along the y-axis, and an hourglass going along the z-axis. That encompasses all the 6 directions in space. So looking at this, we're trying to get a good idea of how to best express the 4 quantum numbers. And this is another way of doing it. We look at, if we remember back from our previous in the video and the previous video, that our number in front of the letter is indicative of our principal quantum number. So we know that carbon is going to be sitting at the final electrons, so to speak, are going to be sitting at the 2p, correct? And then you look at the p or the s, and those letters indicate the angular momentum quantum number. So the last thing we have here is that we need to address the magnetic quantum number and the spin quantum number. So that's what these little lines indicate. These lines are the magnetic quantum number. So in looking at the spin quantum number, you'll note that there is a plus 1/2 and a minus 1/2. And in accordance with the 100 rule, you're always going to have the electrons filling in singly and in parallel, which means that you don't put in both electrons at the same time, and they fill one goes to each of the magnetic quantum number positions, and then they all go up, and then they all go down. So let me demonstrate. So this would be our first electron and our second electron, our third electron and our fourth electron. That seems pretty intuitive, but there are 6 total. We've got 5 and 6. You do not, in accordance with the 100 rule, you have to fill them in singly, which means you fill in one block at a time once you get to that orbital. And then in parallel, which means that they both go, every arrow, if there were 7 electrons, you would have another up arrow. If there were 8 electrons, you'd have a 1 down arrow and 3 up arrows. You simply fill it in singly and in parallel. Okay? So, looking at this, we can now kind of write out the 4 quantum numbers of each of the 6 electrons in the ground state. We know that we've got, let's say we've got electrons, and we've got numbers 1 through 6. 1, 2, 3, 4, 5, and 6. N, L, M sub L, and M sub S. Okay. So now we're going to write those in here. So looking at this, we have one. We have 2 instances of 1, 2 electrons. So we're going to put 1 twice. And then 2, we have 2 electrons plus 1 here and 1 there. So there should be 4 instances where n is equal to 2. And of those, we know that s is 0, and there are 4 electrons total in the s orbitals. So, or the s subshells, rather. So we're going to put 0, 0. We know that when n is 1, L is 0. And then we also know that there are 2 instances where L is 0 when n is 2. And then we know that for P is equal to 1. The angular quantum number signifying P is 1. So, and there are 2 electrons in that instance. So we've got 1 and 1. Now let's look at our M sub L. We've got 1 M sub L here and 1 here, and these are both of them in an instance where they are considered 0. They have to be 0 because the angular momentum quantum number is 0. So the magnetic quantum number has to be 0 in those instances. But what about M sub L? Well, it takes a little practice to recognize this, but you're going to have your P sub X over here. We're going to call this M sub L is equal to -1. M sub L is equal to 0, and M sub L is equal to 1. So in this case, we've got a -1 and a 0. There's 1 electron on the -1 and 1 electron on the 0. There are none on the 1. And then we simply fill it in. We've got a plus 1/2 and a minus 1/2 because our S one s orbital is completely filled, has the 2 electrons it wants. So one has to be going positive while the other's negative. That same is true with the 2s. So plus 1/2, minus 1/2. Now, note in the 2p, both arrows are going up. We're going to call up as plus 1/2. So in both of these instances, these last two, we've got plus 1/2. So that is the 4 quantum numbers for each of the 6 electrons in the ground state. And that is the best way I know of doing it without really having a deep understanding. Once you get a deep understanding, you'll be able to write this without having to draw out anything. But it's always good to look at this in a pictorial representation. And I encourage you to rewind this video and watch it again if you need to. Just remember that your number is going to be indicating your principal quantum number. Your letter is going to indicate your angular momentum quantum number. The rules still apply with that. And you'll note that these little sub markers will be indications of the magnetic quantum number. These ones don't have sub markers, but that's because the angular momentum quantum number is already 0, so the magnetic quantum number can only be 0. Looking at this, now you see that we've designated that because this sub x, sub y, sub z, we gave numerical valuation with the magnetic quantum number as being -1, 0, and 1 respectively. And then looking at the arrows, whether they're going up or down. If they're going up, it's a plus 1/2. If they're going down, it's a minus 1/2. And using the Hund rule, we filled in our p orbital singly and in parallel, which meant that we started out with 2 plus 1/2. If we extended this further, we could get some minus 1/2, but in this point in time, we only have the plus 1/2.